Welcome class to the 6.1 part 1 video of part 1 notes. So this is part 1 notes of 6.1. I'm so excited that we are finally making it to chapter 6. We only have 2 more chapters to go, and we've actually learned all the main concepts. Now we just have some more skills and applications to learn. So you should feel very, very proud of yourselves for making it this far. Okay, so we've put together the idea of antiderivatives and areas under the curve. And don't worry about this slope field part yet. This will come at part 2. And so what we're going to do is tie this all together back with our knowledge of derivatives. So 6.1, really what it's all about is solving these things called initial value problems. And within initial value problems, you have what are called differential equations. You can probably figure out what that is from the title, but I'll go ahead and spell it out for you anyway. A differential equation is basically an equation containing a derivative. That's pretty much what it is. Now sometimes it may not spell it out that it's a derivative, and you have to remember the other kinds of things that are derivatives. So sometimes it might have a rate of change in it. That's a differential equation, something that has a derivative in it. So an example, something that you're going to solve a little later in these notes, would be something like this. So here's an equation right there containing a derivative. And there's the derivative right there. That makes this equation a differential equation. Okay, so we got the differential equation down. It's an equation containing a derivative, which sometimes is disguised as a rate of change. Okay, so then what the next question is, what are initial value problems? Well, it's a special type of problem involving a differential equation, which is why we tackled what that was first. Okay, yeah, sorry. It's involving a differential equation and an initial value. So it's involving a differential equation and an initial value, where we are asked to solve for y. So it's a special kind of problem where we're given a differential equation and we're given an initial value, and we are asked to solve for y. So when we find the antiderivative, which we've already been working with antiderivatives. We've already kind of hopefully noticed some patterns for finding an antiderivative. When we find the antiderivative, we've solved the differential equation part. Differential equation part is solved when we find the antiderivative. When we have found the exact function, which I'll go ahead and call y, when we have found the exact function that satisfies the initial condition, then we've solved the initial value problem. So notice there's 2 parts to an initial value problem. We're going to have to find an antiderivative because that solves the differential equation. But then we're going to have to go a little bit further to get the exact function that satisfies the initial condition. Once we've done that, then we've solved the entire initial value problem. Okay, so there's two parts. finding the antiderivative and using the initial condition to find the exact function. Well, part one, what we're doing today, is focused mostly on finding the antiderivative, which leads to some more notation. Okay, so the indefinite integral basically looks like this. So I want you to, tell yourself what is different about what I wrote here as opposed to what we were doing in chapter 5. Well, I hope you noticed the difference is that it's missing the limits of integration. I have no limits of integration. That is what makes this indefinite. The other kind of integral, which maybe I'll do a little memory cloud over here from chapter 5, memory cloud. Back in the days when we had from a to b of f of x dx, well, we call that a definite integral because it's actually going to have a numerical answer, because this is specifically a certain amount of area below the graph of f of x, above the x-axis, in between these x values of a and b. So this is very definite. Okay, this over here is missing the limits of integration. It's very indefinite. This is not a numerical answer. In fact, the answer to this is a function. Not just any function, but specifically the antiderivative. So if I have a function whose derivative is equal to this little guy, then when I go to do the antiderivative of this little guy, the integral and antiderivative, by the way, are really synonyms. They're really one and the same thing. So I'm going to write over here integral equals antiderivative. Because I can think of an integral as finding the area under a curve, and now that we've done fundamental theorem of calculus, I can also think of it as finding an antiderivative, because it turns out the antiderivative of this curve is also the function describing the area below it. So integral, antiderivative, same thing. So this is the antiderivative of little f of x dx. Well, that would equal capital F, because the derivative of capital F is equal to little f. Okay, but that's not all. This is where we have to be technical. It's very important that we're technical here. I'm going to add a constant. Okay, so this c right here is a constant. And that is because if I took the derivative of capital F of x plus a constant, that would equal the derivative of capital F, because that's what d dx is, it's the derivative, plus 0, because the derivative of any constant is 0. Okay, and we've already agreed that the derivative of capital F is little f. That's kind of the premise here. So it turns out that the derivative of f of x plus c is also equal to little f. So it turns out that little f has an infinite number of antiderivatives, and this expression right here is the set of all of them. So that's the set of all the antiderivatives of little f. So when we're doing an indefinite integral, which is an integral sign with no limits of integration, you cannot leave out that constant. We have to include that constant. And on the AP test, if you include that constant, you get 1 point partial credit. If you leave out that constant, you don't get any partial credit, even if you have other parts of the problem correct. So you got to remember, for an indefinite integral, we have to add c, because, as we found out, If I took the derivative of this, I also get f. So if I'm going to be technical and correct and say that this here is the antiderivative of little f, well, then it could include a constant, and so I have to write plus c, because I don't know what the constant was. I just know that there could have been one there. So you might be wondering or asking yourself, why did we not need the c when we did definite integrals? Why was there no c with definite integrals? I don't know. You may or may not have been wondering this. We didn't worry about this c business before. Why all of a sudden is it important? Well, turns out I was sort of hiding something from you. I didn't quite tell you all of the truth all at once because I didn't want to overwhelm you. But there actually was a c. There was a c here. It just didn't play an important role whatsoever, because this is what happens when I do a definite integral. So let's say I have the integral from a to b. So this is a definite integral of little f of x dx. Well, the steps for this were I had to find the antiderivative and then evaluate it at a and b and then subtract. So let's say I did that. Let's say I found the antiderivative with the constant and evaluated that from a to b. Okay, so I'd plug b into the function, figure out that number, plug a into the function, figure out that number. Oh wait, sorry, and then I subtract. This should be a negative or a minus sign. So you do antiderivative evaluated at b minus the antiderivative evaluated at a. So what do we notice? We notice that I have big F of b plus c minus big F of a minus c, because I have to distribute the negative. And as you see, or as you notice, the constants would eventually cancel out. When you're working with a definite integral, you have to evaluate it at a and b and then subtract. And in the process of the subtraction, the constants would get canceled out every time, which is why they're not even mentioned at all. They're not mentioned in the formula. They're not mentioned at all because they have they don't change the value of a definite integral whatsoever. And so that's why we didn't worry about them with definite integrals. But with indefinite integrals, where there are no limits of integration, where we're not subtracting anything, the c would not get canceled out and therefore plays a very important role with indefinite integrals. So you want to make sure you leave the c there. Don't ever, 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 ever forget the c when you have an indefinite integral, which is an integral with no limits. Okay, now that I have sufficiently emphasized that, we're going to move on to page 2. That'll be our next video.